Hello and welcome back to Precalculus, section 5.3 on infinite amount of formulas. Well, not infinite, but a lot. And because there is a lot in this section, the best way to approach this is through learning the proper way to derive formulas rather than trying to memorize them, or even worse, write them on a piece of paper and then look at them every time you need one, because these formulas are used later on in Calc 2, especially, obviously Calc 3 and differential equations. And yeah, it's going to be annoying to you to have the reference with you all the time to look at them because you don't know them, right? So let's see what is the proper way to learn these formulas and how to deal with everything here. Well, last class we learned the sum and difference formulas, and I did say that you have to memorize those. There's no reasoning with any of that stuff. There are proofs which we didn't cover, but the thing is that
Professor, I can't see your screen that you're sharing.
oh, it's not working. The sharing is not working. Give me 1 second. Aha, that's good. Thank you for letting me know. Is it better now?
Yes.
Awesome. Thank you. Perfect. All right. So now that we fix that, let's see which way we deal with formulas. So first of all, last time we learned, that say sine of x plus y was sine x cosine y plus cosine x sine y. That's what we learned last time. And let's pretend for a second that you memorized and learned this one and 100%, right? If someone shakes you out of bed at 4:30 in the morning and asks you this, you just, right, immediately answer because you know it so well. So let's pretend that's the case. What would be the formula for a double angle in that case? Well, since you know the formula above, you can immediately write 2x as x plus x, and then sine of the first, cosine of the second, plus cosine of the first, sine of the second. But both of those, what I call first and second angle, are both x and x, right? So this ends up being sine 2x is just 2 sine x cosine x. I used this formula many times this semester in Calculus 1 and differential equations. And when I teach Calculus 2, again, million times. So this formula is very frequent. And as you can see, it's very easy to, it's easy to remember the formula as well, but it's very easy to see where the formula comes from, right? Because all you need to do is what you learned last class. Instead of writing it as sine x plus y, you write it as sine x plus x, and you apply the same formula. So with that, right, now that you know the trick, you can derive the cosine and the tangent using the same ideas. So your cosine 2x will be cosine squared x minus sine squared x when you combine all of those things the same way. And tangent 2x will be 2 tangent x divided by 1 minus tangent squared x. So these formulas, as I said, you learned them as x plus y last class. Now you just change those x plus y into x plus x, and you would have your 2x, which is called the double angle formulas. Notice that we do not bother with secants and cosecants and stuff because this is enough for us. and if you need a secant, you just write it as 1 over sine. So it's very easy. Sorry, secant is 1 over cosine. Ha. So these are the double angle formulas. And when do you use double angle formulas? Well, again, to compute values or in identities, to transform equations and a whole bunch of other stuff where they show up. Now, computing numbers, right? The double angle formula is going to be used for something that you don't have the values for, given in your basic 0, 30, 45 degree, 60 degree, and 90 degree, right? So we'll see the examples when we get there. Now let's take a look at other formulas that we want to have here. First of all, I'm going to take, and this is a very important part, I'm going to take this double angle cosine, and I'm also going to remind you that sine squared plus cosine squared is equal to 1. And that you can flip that one into sine squared x is equal to 1 minus cosine squared x, and cosine squared x equals to 1 minus sine squared x. Now, I hope you see where this is going, because I can replace these one at a time, obviously, by those. So let's go, let's say orange. If I replace the sign, what do I get? I get cosine 2x is equal to cosine squared x minus, and when you replace the sign, you get 1 minus cosine squared x. When you follow the algebra, you remove your parenthesis there, you get 2 cosine squared x minus 1. Aha. So now that's another formula for cosine of the double angle. And this formula only uses cosine. It doesn't use sine at all. Right? So now I have this formula for double cosine, which says cosine squared minus sine squared. But then I also have this for the same double angle. And if we replace this one, you get that the cosine of 2x is equal to 1 minus sine squared x minus sine squared x, which is, right, that will be your cosine and minus, cosine squared minus sine squared. And when you get rid of the parentheses, you get this. So that's what we have as two alternate formulas for double angle cosine. And as you can see, I'm deriving all of these formulas. I don't need to, memorize them or anything like that, because it's derived from the formula that we should all know. It's a basic trigonometric identity called Pythagorean identity. You know your Pythagorean theorem, right? A squared plus b squared equals c squared. This is the form of that theorem written in trig language. So that's why we can easily manipulate and change these formulas. Now, why have I done this? Well, if you observe these two, they have a very interesting feature. Single cosine on one side, cosine squared on the other side. Single cosine on one side, sine squared on the other side. This is where the power reducing formulas come from. Power reducing formulas are the flips of these. So now we derived these, the orange and the purple ones, as alternate forms to this one. And usually in textbooks, when you look in the formula sheet and so on, even go online and look at the formula sheet, you are going to find all three of these formulas listed under cosine 2x. And I believe our book does the same on the back cover, I believe. And yes, they do. So if you look at the hardcover in the back of the textbook, the double angle formulas, cosine is in the middle, and it lists all three of these forms. Calculus book does the same, and so on. So most of the books, right, and literature will list all three formulas, not just this form, right? But these two in addition to that. So now, when we move to double angle, sorry, not double angle, power reduced formulas, we take these cosine 2x equals 2 cosine squared x minus 1, and we just, using algebra, rearrange this to solve for cosine squared x. So what do you need to do? You have your cosine 2x plus 1 equals to 2 cosine squared x, and from there you get your cosine squared x is equal to cosine 2x plus 1 over 2. And that is your first power reducing formula. You can see that the cosine squared is reduced down to the single cosine. It's a really cool feature. And then if you flip the other one, 1 minus 2 sine squared x, you will get the power reducing formula for sine. So the power reducing formula for sine is you move sine to the left, becomes positive, and then you divide both sides by 2, which gives you the power reducing formula for sine. Now, usually in the books, they write this one in front so that it kind of follows the same format like this formula, but these two are power reducing formulas. Absolute must to know to pass certain problems in calculus, because especially that if you have for calculus, I know you're not doing integration yet, but doesn't matter. There is a concept called integral, and if you get this question, the only way you can do it is through power reducing. There are no other ways. So if you don't know the formula for pre-calc, you can't do calculus 2 problem, and then you are stuck, right? Or calculus 1 actually. It's also in calc 1. So these two formulas are the power reducing formulas, and you can easily obtain the tangent as well, because you just need to divide sine with cosine. So you'll get 1 minus cosine 2x over 1 plus cosine 2x. That's easy. And you can just say over here, tangent theta equals sine theta over cosine theta. That's how you get that formula. Now, power reducing for tangent is not really used too much, so you don't have to stress. I mean, sure, you're going to have problems in your homework and so on, but later on, right, it's sines and cosine, the power reduction that you really, really need. So it's better to learn it now. So how many formulas so far? 6, right? We have 6 formulas so far. We have 3 for double angle and 3 for power reducing. The only 3 that are left are the 3 half angle formulas. But then, hold on. Aren't these already half angle formulas here? Because if you take a look at the angles, on one side you have 2x, on the other side you have x. Well, that's half to me, right? X is half of 2x. So we can technically come up with half angle formulas by flipping the power reducing formulas. Just algebra. And as you can see, we derived the whole lesson from a single cosine 2x formula, which is amazing to me. I mean, when I saw this for the first time, I was blown away. I always get excited when you don't have to memorize things. You can just reason with them and, you know, go from one to the next formula easily. So you have your, let's say, sine squared x formula as 1 minus cosine 2x over 2. So what you can do is you can use the substitution. Two x equals theta, which makes x equals theta over 2. And you can plug that in here. So you will get your sine squared of theta over 2 is equal to 1 minus cosine of theta divided by 2. And your half angle is just a square root of 1 minus cosine theta over 2. And then, because you were taking the square root of both sides, you will put plus minus in front. Like, can it be easier than this? You just square root both sides. Now, granted, yes, there is the substitution method to kind of see that this is half of 2x. I mean, it doesn't take nuclear science degree to see that, but still, I think this is very straightforward. One red. There we go. So that's one of the half angle formulas, and you can get the other one in the exactly same way. You have your cosine squared x is equal to 1 plus cosine 2x over 2. Use the same substitution, where 2x is theta, from where x is theta over 2, and just plug them in. So cosine squared theta over 2 is equal to 1 plus cosine theta over 2. And now, when you apply square root to both sides to kill the square, you have cosine theta over 2 is equal to plus minus square root of 1 plus cosine theta over 2. And that's the second one. The third one, which is tangent, is always sine divided by cosine. So tangent theta over 2 is sine theta over 2 divided by cosine theta over 2, which is plus minus square root of Sine goes on top, so minus 1 minus cosine theta divided by 1 plus cosine theta. And that's it. We have all 9 formulas that we need to survive identities and Calc 2 later on. So let's list everything on one spot. Kind of also the good way of reviewing them all. Sine of the double angle is 2 sine x cosine x. Cosine of the double angle is the cosine squared x minus sine squared x, or 2 cosine squared x minus 1, or 1 minus 2 sine squared x. So those are the 3 variations. We derive them here, right? The orange and the purple. So those are the two methods, two extra formulas. Good. And then we had sorry, we had the tangent, which was tangent 2x was the 2 tangent x over 1 minus tangent squared x. From the double angle formulas, we went to power reducing. Sine squared x is equal to 1 minus cosine 2x over 2. Cosine squared x is equal to 1 plus cosine 2x over 2. And finally, tangent squared x is equal to sine over cosine, so 1 minus cosine 2x, 1 plus cosine 2x. And those would be, as you can see, power reducing, because on the left you have a square, on the right you have no exponents. And finally, half angle formulas. So sine of x over 2 is equal to plus minus square root of 1 minus cosine 2x over 2, no, cosine x over 2. Cosine of half angle is plus minus 1 plus cosine x over 2. And finally, tangent of half angle is going to be plus minus square root of sine divided by cosine. There we go. That's 8 formulas. And all of them came from cosine double angle, which is amazing. So this is it for the section, right? In terms of introducing new stuff. Now we just have to focus and do some exercises in this particular section. I know it's a lot of formulas, but it's a lot of formulas if you're forcing memorization. If you use the rationale to get to them, it's much easier. Again, I'm not going to tell you how to live your life, right? So you will pick your poison. If memorizing 9 formulas is what you do and what you're good at, and you know that that's going to actually stay memorized for a couple of years until you're done with calculus and whatever other engineering courses, then yeah, I guess that's your way. But we are all different snowflakes, right? So let's take a look at examples and see what they have in store for us. Verify. Yeah, verify identity. That sounds good. So we have. Let's compute the values first, because let's compute values, and then we'll figure out the rest. Um, they give you a triangle. Oh, they give you a Pythagorean triplet, 3, 4, 5. 3, 4, 5 triangle. And they want you to write a whole bunch of stuff for it. So they're interested in sine 2 theta. They're interested in cosine 2 theta and tangent 2 theta. Not a problem. Well, first you have to get through the triangle. So 3 is opposite, 4 is the adjacent, and 5 is the hypotenuse. That's the longest side. And once you have those, you can write that sine of theta is 3/5. Cosine theta is 4/5. And tangent theta is 3/4. This is your first lesson in trig, right? To be able to write trigonometric functions looking at the opposite, adjacent, and all that good stuff. The SOHCAHTOA, as you would say, right? SOHCAHTOA. So let's go. Let's solve the problem. What do we have? Sine 2 theta was 2 sine theta cosine theta. That's 2 times sine theta is 3/5. Cosine theta is 4/5. All together 24/25. Done. Cosine 2 theta. Now you can use the cosine squared minus sine squared, or the other two. Doesn't matter. You will get the same value. So now cosine squared, that's 4/5 squared, minus sine is 3/5 squared. So that's going to be 16 minus 9 over common denominator of 25, and 16 minus 9 is 7 over 25. And finally, tangent. Now, you can get the tangent by simply dividing sine 2 theta over cosine 2 theta, so you don't even have to use the formula over there. It's 24/25 divided by 7/25, and that is when 25s would cancel, right? You get your 24/7. And there they are. So now the whole question is on the screen. And as you can see, they're asking for the value of sine 2 theta or cosine 2 theta. And they gave you the triangle with numbers. Questions, concerns, anything regarding this problem? Okay. If not, then we're going to move to the next problem. The next problem is interesting because the values you get are not in your chart. 2 tangent pi over 8 divided by 1 minus tangent squared of pi over 8. Well, this is the double angle. So we have that this is equal to tangent of 2 times pi over 8, which is tangent of pi over 4, and the tangent of pi over 4 is 1. So there's a cool way to write 1, right? You can write it that way. Now, where does this come from? It's the formula backwards. Right here. So we had the right-hand side, and then we condensed everything into the left-hand side. Now, since x is equal to x, right, and you have 2x, it's tangent 2 times pi over 8. 2 times pi over 8 is pi over 4. All right, let's see. Maybe you should try one of these, or a couple of these, whatever. So here is the right triangle, and that's angle alpha. This is 24, this is 7, and they're asking for tangent to alpha. So you need the third side, and you need to set up your trig. So let's see what you get. Try this one on your own for a few moments. All right. So what is the third side that it's what is the measure of the third side that it's missing?
I got 25.
25. Good. So this is another one of those Pythagorean triplets. So that's 25. And we set up our adjacent, one that is touching the angle, opposite, across, hypotenuse. It's the long side. And tangent. Actually, wait. For a tangent to alpha, we didn't even need that 25 when I think better, right? Because the tangent has, right, the tangent formula does not use the you don't have to go through sine and cosine. You can just use the tangents, right? So 2 tangent theta divided by 1 minus tangent square theta. So we actually don't even need this. I don't know why I told you. See, I'm not thinking. Yeah, I'm not thinking. Tangent to alpha. I have thetas there and alpha on the left. Alpha, which is our A, but in Greek. So 2 times tangent is 7 over 24. There we go. 1 minus 7 over 24 squared. So what we have here is we just need to simplify this. Now the way to simplify this quickly is to multiply by 24 squared so that you can kill the double fraction. And what you have is 2 times 7 times 24. One of the 24s will cancel. And over here, you have 24 squared minus 49, well, 7 squared, which is 49. We'll calculate that in the next. So tangent to alpha is equal to what? You have your, I'm just trying to see if anything is going to reduce, but no. We can plug everything in a calculator and see what we have. So that's 14 times 24 is 336, and 24 squared minus 7 squared is 527. And that will be it. It doesn't reduce, right? Because one is even, one is odd. The bottom number is not divisible by 3. Yeah, that shouldn't be. Yeah, it's not going to reduce to anything. That's the end of the road for that question. Let's take a look at some of these identities. That last identity in the last class was a little bit spicy, but eventually I got it, which was cool. Now let's see if we run into some heavy hitters this time. So this is the identity. Let's see what you get. Try it for a few minutes on your own. All right. So we know the formula for the tangent, right? Because that's given. But we don't know the formula for the cotangent, right? That one is not given to us. And but we know that cotangent is 1 over tangent. So hopefully we can work out something with that. Now let's see. So tangent was when you take a look at the half angle formulas, they're the same like the power reducing. So the first one would be the square root of 1 minus cosine x over 1 plus cosine x minus, and this one will be flipped, plus cosine x over 1 minus cosine x. Now, there is nothing that we can do on the other side other than write it as a cosine over sine, which for now we don't have to worry about. So what should we do with the left side? Well, first of all, in order for you to find the common denominator here, right, you need to separate the square roots. Cosine x over square root of 1 plus cosine x. So each one of these gets its own square root. That's a basic algebra rule. We're not doing anything special there. But then we multiply by the square root of 1 plus cosine x and 1 minus cosine x so that we can have common denominator. So on top, we are getting 1 minus cosine x, everything squared and square root, so they cancel, minus the same thing here, 1 plus cosine x on that side. And on the bottom, we have the square root of 1 minus cosine x, 1 plus cosine x. Great. So what do we have on top? If you remove the parentheses, you have 1 minus cosine x minus 1 minus cosine x. And when you FOIL in denominator, you get 1 minus cosine squared x. Nice. Perfect. 1 minus 1 is gone, leaving us with 2 cosine x on top, and on the bottom we have a square root of sine squared x, and there you have it. Negative 2 cosine x over sine x, which is negative 2 cotangent x. That was a nice friendly identity. All of the steps were visible and common sense, and there was a flow, right? Because you just say, all right, let me just write these out, and we wrote them what they are, right, to remove the half angle. And then when you get here, you have two fractions that are subtracted, so you find common denominator for it. That will be the next logical step. So the whole problem, the flow, was just absolutely perfect. This was actually a good exam question because it has a very nice flow, and there were no dirty tricks or something that you had to, like the previous class at the end. That was hard to see. I mean, it took me some time, but I got it. And that was a good lecture in never give up, right? But this problem doesn't have anything special to it. Everything is just a perfect flow from one step very clearly to the next of what you're supposed to do, because the most natural thing to do at each step was right there in front of us, right? Get the common denominator, get those parentheses removed, and then subtract those 1 multiply under other root, distribute, or FOIL, actually you say FOIL, right? And get that 1 minus cosine squared x, which is sine squared x. The root cancels at that point. Cosine over sine is cotangent. Absolutely amazing problem. I picked a random and there we go. It worked out great. Let's see another identity. Oh, okay, 29. I have no clue if this is gonna be spicy or not, but let's see. Cotangent x is equal to sine 2x over 1 minus cosine 2x. It shouldn't. I mean, all right, so try this one for some time, and then we'll get together. Okay, let's take a look. Every time, as I said, when we did the basic identities, pick the more complicated side and try to simplify by using the identities, right? So we pick sine 2x over 1 minus cosine 2x, and we expand to see what we can get. Now, I didn't teach these formulas. They're there. I think they're somewhere in a book. This is actually the half formula for tangent. Yes, half angle formula for tangent. There is a very easy hack way to solve this problem. I'm going to outline this in a corner here, and then we're going to try to go through the identity. So if you take a look at this formula, tangent x over 2 is equal to 1 minus cosine x divided by sine x. And you just use the substitution. Theta equals x over 2, from where x is equal to 2 theta. You can see that you can get tangent theta is equal to 1 minus cosine 2 theta over sine 2 theta. And then when you flip tangent into 1 over tangent to make it into a cotangent theta, the other side flips and the problem is solved. But that one requires to memorize the half angle, the alternate formulas for half angle of tangent. They're given in the book, yes, right? But it's just more stuff to memorize. Let's see if we can deal with this problem without that. So the problem is solved. There you go. But let's see what can we get without it. So how about sine 2x, sine 2x is 2 sine x cosine x, 1 minus, and then for this one, let's use 2 cosine squared x minus 1, or 1 minus, it doesn't matter. So the top is 2 sine x cosine x, and on the bottom, when I get rid of the parenthesis, I get 2 plus 2 cosine squared x. Now I can factor out 2 in the denominator and have 1 plus cosine squared x there. So these guys now cancel. And let's see. Oh, that's a minus there. Oops. That's a minus because when you apply -1, it becomes -2 cosine. There we go. And now this is just sine x cosine x divided by, and 1 minus cosine squared x is sine squared x. So sine x and 1 of the sine x cancels, and there's your cotangent x. It can be done without these special formulas, as you can see. Okay, let's compute the value, and or maybe 2, and go from there. So tangent of 75 degrees. All right, so I would propose, so you can practice, to solve this problem in 2 different ways, as the sum of 2 angles, and then as a new one as a half angle. So 2 ways. Way 1, half angle, and let's go blue. Way 2, sum of 2 angles. So let's see which one And they both should give us the same answer at the end, right? So let's see what you guys have for this. The sum of two angles obviously was in a previous section, right? The last class. And then you have this one now. I'll give you some time to practice this, and then we'll continue. All right, let's take a look. So half angle should be fairly straightforward and simple, right? We have, so that's the first one. So what do we have? We have 75 is equal to half of 150. And 150 is angle that we can compute for tangent, right? Degrees. 75 degrees is this one. This won't go. There we go. So now, when I um, write this, it will be actually tangent of 150 over 2. And then we use our tangent of a half angle formula, which is the square root of 1 minus cosine of 150 degrees divided by 1 plus cosine of 150 degrees. And cosine of 150 degrees, we can calculate, right? We know it's in the second quadrant, and we can calculate the reference angle and all of that good stuff. So 150 degrees will be 30 degrees away from 180. That means that the reference angle is 30 degrees. And the cosine, all students take calculus, right? Cosine is negative in second quadrant. So this is equal to the square root of 1 minus negative cosine of 30 degrees over 1 plus negative cosine 30 degrees. Because, again, reference angle in the second quadrant for cosine, reference angle is 30, because, right, 150 plus 30 is 80, 180. And cosine is negative in the second quadrant, only sine is positive, right? So we have negative cosine of 30, and that becomes 1 plus. Now, cosine of 30 degrees is root 3 over 2, divided by 1 minus root 3 over 2. And now when we multiply both of these by 2 to get rid of the double fraction, you will have 2 plus root 3 divided by 2 minus root 3. Now, you can rationalize and keep working with algebra. I want to do the other one as well. So 2 plus root 3 over 2 plus root 3. That's happening under the root. So I'm technically multiplying by 1. And if you look on top, I'm not going to FOIL it because it's going to stay squared. And on the bottom, when you FOIL this, you get 4 minus 3. So you separate the two roots because we have that algebra rule. And you just get 2 plus root 3. Algebra rule that separates roots, I hope you remember it and know it, right? That when you have square root of a fraction, each one gets its own. So that was the way one to calculate 75 degree tangent of 75 degrees using the half angle formula. Now what we did, not yesterday, the last class, we did tangent of 75 degrees can be written as tangent of 30 degrees plus 45 degrees. That's 75, right? So we can do sum of two angles, right? And that was the formula where we had tangent of each. So 45 degrees there. Divided by 1 minus the multiplication of tangents. So tangent 30 degrees, tangent 45 degrees. So that was the formula from last class. And now that should simplify into this, hopefully. Right? Otherwise, we broke mathematics and we can go home. Tangent of 30 degrees is root 3 over 3. And tangent of 45 is 1. 1 minus root 3 over 3 times 1. I need this line to be that long. So when you multiply now top and bottom by 3, there we go, we get root 3 plus 3 divided by 3 minus root 3. We rationalize this by 3 plus root 3, 3 plus root 3. And in the numerator, we have root 3 plus 3 squared. And in the denominator, we have 9 minus 3, which is 6. So now, in the numerator, when we square this, we get 3 plus 6 root 3 plus 9. And in the denominator, we have 6. That's 12 plus 6 root 3 over 6. And then 12 divided by 6 is 2. 6 and 6 cancel. Root 3. And there's your 2 plus root 3 like we had before. So this problem can be done through half-angle formula, which is what we just learned, or it can be done through addition of two angles because we had 30 plus 45 to make 75. Now, you're not always going to have possibility to do it with basic angles. I've seen another problem which said something with the decimal. For instance, 22.5, right? 22.5 is half of 45, so you have to use half angle formula there because you cannot make 22.5 in addition and subtraction of those base angles, right? 30, 45, 60, right? They're not gonna add or subtract into a 0.5 somehow. So you have to use half angle formula on that one, for instance. So in some cases you have to use the half angle formula, but as you can see in this particular case, we can do both. And it was a good exercise. I mean, this is more algebra than anything else. It's just shoveling terms around and being able to, right, remembering the rules of square roots and all of that basic algebra. Any questions, concerns regarding our 9 formulas we learned today? So we have a half angle, we have double angle, and we have the power reducing. All right, so no questions. Great. I will see you then in the next lecture.